Hi, my name is Valentin Hartmann. I'm a PhD student at EBFL, and I'm looking forward to presenting to you differentially private propensity scores for bias correction, short DiPPS, our method for mitigating participation bias. This is joint work with Liang-Wei Chen, my supervisor, Bob West. As the cartoon illustrates, when asking people to share their data, you will only get the data of those who aren't concerned about sharing it. This becomes a problem whenever the things that we want to measure in the data are correlated with the willingness to share data. There are many instances of this in the scientific literature. To just name a few, people who had a more liberal attitude towards sex were more likely to participate in a survey about sexual behavior. In a study on sick leave of employees, those who were on sick leave less often were more likely to participate. In those examples, shame seems to be the main driver behind people's response behavior. But concerns about privacy can also directly be associated with what one wants to measure. Throughout this talk, we will use the following example. A browser developer offers users the option to share user statistics with them in order to measure the popularity of different features and thereby improve the browser. Some of the features of modern browsers are privacy-related, for example, tracking protection or the private mode. Users who are more concerned about their privacy will use those features more often than users who are less concerned about their privacy. Users who are more concerned about their privacy will also be less likely to participate in the browser developer's data collection program. Browser developer will thus underestimate the popularity of privacy-related features. DiPPS, our method, allows one to correct for this bias. The basic idea is the following. We have a group of individuals who are willing to give us their data, which we will call participants. We have another group of individuals who are not willing to give us their data, the non-participants. We convince as many non-participants as possible to give us a small aggregate piece of information about their data. For this piece of information, we offer those individuals a strong formal privacy guarantee in the form of differential privacy. We then use the information collected from the non-participants to de-bias the data of the participants by reweighting it. It's a small teaser. DiPPS also works in other settings as the one described here. I will come back to that later. The privacy guarantee that we offer to the non-participants is a strong and well-established one. It has previously been used by organizations such as Microsoft, Google, or the US Census Bureau. Differential privacy is a technique that allows one to collect aggregate information about the user population. However, by adding random noise in the process, it prevents the data collector from learning any significant amount of information about any particular individual who participated in the data collection process. We haven't yet touched upon how exactly the reweighting of the participant data works. There's the data of the participants and the non-participants, where each participant and each non-participant has exactly one data point. In the browser example, the data point would be a vector where each entry corresponds to one feature of the browser. It counts how often that feature has been used by the individual. As you can see, the two data distributions differ. We only have direct access to the participant data. We want to use some differentially private information about the non-participant data to reweight the participant data so that the reweighted dataset more accurately represents the overall data distribution. To this end, we fit a clustering model to the participant data. We then ship this clustering model to the non-participants. Each non-participant determines the cluster that the data point lies in. We send this information back in a differentially private way. Aggregating this information then allows us to estimate the cluster weights of the non-participants. Finally, we use these weights to reweight the participant data so that this distribution more closely matches the distribution over all individuals. We do this by computing the propensity of each data point coming from a non-participant, hence the propensity scores in the name of DiPPS. Let's come back to the example from earlier. There, the reweighting would result in the browser developer increasing their estimate of how often the tracking protection feature is used. We validate DiPPS on various datasets, from browsing histories to financial data and food purchases. split the data into participant and non-participant data based on potentially sensitive attributes. For example, for the food data, we assume the participants are those that do not receive food stamps, and the non-participants are those that do receive food stamps. In the first three of these tables, we see the mean average error made when estimating the mean, the variance, and the median, the attributes in the data. In the last table, we see the Wasserstein distance of the estimated versus the true data distribution. We compare the bias correction of DiPPS with a naive approach that only uses the participant data to draw conclusions about the entire distribution. As we can see, for essentially all datasets and all metrics, DiPPS manages to reduce participation bias. To conclude, DiPPS allows for reducing participation bias. It does this by collecting differentially private cluster information from individuals that are not willing to share their raw data and using this information to reweight the participant data. As promised in the beginning, there is another setting in which DiPPS can be applied as well. Assume that the data is so sensitive that none of the individuals is willing to share their raw data. In that case, we can replace the participant data with a public proxy dataset. For example, if you want to collect statistics about private messages, you can use public conversations from Twitter as the proxy data. This concludes my talk, and I'm happy to receive questions now.